Let's practice with a two-dimensional kinematics problem with a horizontal only initial velocity. So let's set up the following scenario. Um, Bob is standing here, got a big water balloon in his hand, and he's going to throw it. And over here stands his friend Alice, who is really cute, and he sort of has a crush on, but he doesn't want to tell it. And since he happens to be in the third grade, he's going to show his love for Alice by throwing a water balloon at her. But he does love her and he doesn't want to hurt her, so he's going to throw the water balloon perfectly horizontally, and he wants it to just hit her feet. So the ball's going to come over here and just land right on her feet and get her shoes wet, but not hurt her, and it'll show how much he loves her. Okay, so this is a perfect sort of life lesson again, which is sort of what we're all about in this class. Initially, let's say that the ball is 2 meters high, or the water balloon, I mean, is 2 meters high, and because he's got it above his head to throw it, and Alice is standing a distance of 20 meters away. Okay. The key question here for Bob is how hard does he have to throw it? Because obviously if he throws the water balloon too hard, it will hit Alice in the face, and that would be embarrassing. If he doesn't throw it hard enough, it would fall short, and Alice won't even know what's going on. So, Bob has a really important dilemma on his hands. So really what I want to know is what initial velocity is going to be required. Okay, and remember that this is a sort of a simplified problem, so we're going to require that this be horizontal only, right? Zero y velocity, so horizontal launch. Okay, so what's our process? Our process is to write down all our variables, everything we know, v0, v, a, t, delta x, and again, because it's two dimensions, we're going to have an x component and we're going to have a y component, and we're going to put our coordinate system right here, x and y, so that we're starting at the bottom. Okay, so what do we know? Do we know the initial velocity in the horizontal direction? No, that's actually what we're looking for, right? We're looking for this initial velocity in the horizontal direction. Do we know the final velocity? No. We do know the acceleration. Remember, we get the acceleration for free. In the horizontal direction, the acceleration is 0, not speeding up or not slowing down. We don't know how much time it's going to take, but we do know how far the water balloon has to travel. It must travel 20 meters, so that's going to be a requirement for ours. 20 meters of horizontal travel. Positive or negative? Well, the ball or the water balloon is traveling forward, so it's going to be a positive 20 meters of travel. In the y direction, we made a requirement that this was a horizontal only launch, so the y velocity is 0. It's not moving up or down at all here, it's moving perfectly horizontally. We get, again, for free the acceleration of negative 9.8 meters per second squared because we're near the surface of the earth, and it's down. We said over here up is positive, so down is negative. And again, since we know the initial starting height, the change in y position is going to be 2 meters, but this time the change in y position is going to be negative because we're starting high, we're ending low, so we're losing distance. This is what we know. Ultimately, what we're looking for is this initial horizontal velocity so that Bob can show his true love. What is our process? Our process is we know 3 things in the vertical column, so I'm going to calculate the others. In this case, I know v0a delta x, so I'm going to say for the vertical problem, or the y problem, delta x equals v0t plus 1/2 at squared. Negative 2 meters equals 0 because the v0 is 0, plus 1/2 times negative 9.8 meters per second squared times t squared, which we don't know. So negative 2 meters equals negative 4.9 meters per second squared. T squared is going to be equal to 2 divided by 4.9 is 0.408. My meters cancel out, so I just get seconds squared. So my time is going to be equal to the square root of 0.408, which is going to be, since I've taken a square root, I always do plus or minus 0.639 seconds. And of course, we don't like to time travel, so we're going to choose the positive. So the time that it takes is 0.639 seconds in order for something to fall 2 meters, right? We're only doing the vertical part of the problem, so that would be the same as if I just dropped the water balloon straight down. It would take 0.639 seconds. It also takes 0.639 seconds to fall from that zero gravity line. We know that the time is shared, 0.639 seconds, and now I know three things here. So I can do the vertical, I did the vertical part, I can do the horizontal problem, or the x part of the problem. Delta x equals v0t plus 1/2 at squared. In this case, delta x is 20 meters is equal to v0 times 0.639 seconds plus 1/2 times, acceleration is 0, t squared. So this whole term goes to 0. So I end up with v0 is equal to 20 meters divided by 0.639 seconds, or v0 is equal to 20.639, 31.3 meters per second. So, if Bob gives his water balloon a perfectly horizontal velocity of 31.3 meters per second, that water balloon will hit Alice on the foot if she is standing 20 meters away. One thing to think about might be, is this possible? Is this realistic? Is it possible for Bob, the third grade love machine, to throw a water balloon at 30 meters per second? Well, you can convert that to miles per hour if you wanted real quickly. 30 meters per second, and there are 1,600 meters in a mile, and there are 3,600 seconds in an hour. Convert that to miles per hour to figure out if that's realistic or not. Is it possible? I mean, is that a hard throw? Is it an impossible throw? Is it realistic? And you can make that decision. So this is another example of how to break up the vertical and the horizontal components in a two-dimensional trajectory problem.